Hello, hello. Welcome. Hopefully, everyone can hear me and see me okay. I think I've sorted out my screen. But hello, welcome. Please say hi in the chat if you're here. I'm just going to make sure that everything is looking all right. Is good. Welcome. So this is one of our A-level chemistry Sunday sessions. So every Sunday we do, or approximately every Sunday, we do a revision session on either chemistry, physics, biology, or maths. This is one on chemistry. We're going to look at moles and mass, one of the fundamentals of chemistry, something that hopefully you've had an experience of in GCSE. GCSE, if you're in year 12, if in your year 13, you've probably experienced quite a lot of moles and mass and using it. I think if you're in year 13, sorry, I think I said that, then you've probably experienced a lot of it. If you're in year 12, you've probably experienced it in GCSE and are just realizing how much you're going to be using it in A-level chemistry. So there's a lot of the mathsy kind of side of things, but it's not actually maths. As we'll see here, we do a lot of looking at ratios. So there's a lot of ratios of things. So we'll get started in a min. We'll just give people a chance to arrive. So hello, please feel free to say hi if you're here. Feel free to say hi in the chat. Welcome if you are new to the channel or new to our Sunday sessions, and welcome back if you've been here before. If you haven't already, hello Fazia, lovely to be here again. Welcome. If you haven't already, please feel free to download today's slides. You can keep them on your computer or you can print them out. You can use them to make notes. You can follow along. You can keep them for revision at a later date, whatever works for you. So yes, please do that. And we will get started. The best way for you to, or the way you're going to get most questions is if you engage with them. And I know that sounds easier said than done, but have a go. Even if you don't write in the chat, do have a go at answering any of the questions that I vocalize. Even if you think you might be wrong, have a go and see what happens, because worst comes to worst, you at least find out what you don't know. And if you realize you don't know something, that gives you something to work on. And you can then improve on that for next time. So I'm just going to fold over my screen. Sometimes when I do this, my camera turns off. So we'll see what happens this time. No, looks like we're okay. Good. Okay, so let's have a look at maths and moles and maths. So before we do, sorry, a little bit about me. I am the lead chemistry teacher at Snaprovise. I'm the only chemistry teacher at Snaprovise. I've got PGC chemistry education. I've been teaching science for over 8 years, but my specialism is chemistry. So I've got a PGC from Oxford in science teaching, but specialising in chemistry. But I do love all of them, but chemistry is the best, even if I do say so myself. So for this session, we are going to aim to perform calculations with moles and molar mass. We're going to look at performing calculations with Avogadro's constant, and we're going to look at understanding and working out molecular and empirical formulae. We're not going to look at balancing equations, how to do that or anything like that, because that's covered in a different web class. So that you have to do by yourselves if you're not confident. So we tailor these web classes to suit all 3 of the main exam boards, AQA, EdXL, and OCR. So if you're an AQA student, these are the spec points that we're going to be covering. If you're not comfortable and confident in navigating your own specification, I would highly recommend, if you take away anything from this session, it's that you get comfortable and confident with looking at your own specification, because as we'll see, they vary considerably across exam boards, but they're very specific. And they tell you exactly what you need to know, the wording that they like to hear, how detailed the explanation needs to be, etc. So get confident with your specifications. So if you're AQA, it's these spec points that we're going to be looking at today. If you're OCR, it is these. And so just to kind of prove a point, OCR, especially within the mole, and amounts of substance sections gives you the definitions they're looking for. So if you're looking for the definition of an empirical formula, it's written here, the simplest whole number ratio of atoms of each element present in a compound. So they have literally told you in your specification the wording they want to hear from you. So double check that. And then at Excel, it is these. The specifications do vary between examples, but where there are major differences, we will point them out. Okay, so let's start off by thinking about what we should already know, either from the beginning of year 12 chemistry or from GCSE. So we need to know the definition, a written definition of relative atomic mass. Does anybody know what they think that is? Do you want to have a go at writing it in the chat? I'll give you a minute and then I will get started. So what is relative atomic mass? Or if you're not sure what relative atomic mass is, do you maybe know what molecular mass is? Could you put that in the chat? And again, if you're not 100% sure on the definitions, maybe you could just describe them to me or give me an example of where we might use them or where they might be useful. And then finally, what is an ion? I need to know what an ion is or how to recognize an ion, or how to define an ion. So can you pop that in the chat as well? Any one or two or three of those would be lovely. I'll give you a minute while I slurp my tea and then we will get started. So we do need to know these definitions off by heart, particularly the first two, because you could be asked them. Now, there are some varieties in wording. Most of the time they will give you, they don't mind a little bit of a variety in wording as long as you get them key points across all the examples. So with relative atomic mass, there are a couple of things which I'll underline that you need to make sure you get into your definition in the correct way. So I'm going to write it like this. Relative atomic mass is the mass of an atom relative to 1/12, that's 1/12, sorry, the mass of an atom of carbon-12 something like that. And then I also have to get in there that it's an average or a weighted average mass. So you could put the weighted average mass of an atom relative to 1/12 the mass of an atom of carbon-12. You don't have to say an atom of, you can just say of carbon-12. But we also need to make sure that we are aware that it's a weighted average of isotopic masses. Weighted, oh, can't spell, let's try that again. Average of isotopic masses. So key phrases here, that relative to 1/12 the mass of carbon-12, and that it is a weighted average of isotopic masses. But you can say of all isotopes of an atom, that would be fine as well. But sorry, all isotopes in an element would be better. So you need to also include that it's to do with isotopes as well. So the key bits are the underlining. You need to make sure you say something about those bits in your definition. Okay, molecular mass. Molecular mass. So in its simple terms, it's the mass of a molecule, as in molecular mass, it's the mass of a molecule. But we can also describe it as the sum of the masses of all atoms of each element in a molecule. The key point being that it is the whole of the molecule, it's the mass of the whole of a molecule, not just kind of one of each atom or anything like that. Oh, cool. And then an ion, quite simply, is just anything that is a charged particle that consists of an atom or bigger. So I'm not talking, you can't call an electron an ion, you can't call a proton an ion, but you could call sodium plus an ion. You could also call CO3 2- an ion. So it's got to be an atom or a molecule that is charged. Let's put it the other way around. Is a charged atom or molecule. But again, you could say that it is an atom or molecule that has an overall charge or something like that, or does not have a neutral charge. That would also be fine. Okay. I forgot to underline that one. Cool. Right. Let's have a think about moles then. Something we should all be comfortable with, but just in case we're not, we're going to do a quick revision and make sure that we know all the key bits. So what is a mole? So in the same way that this is the thing that kind of gets most students, especially when we introduce a subject, in the same way that we can say a dozen eggs and we know that a dozen, which means 6, or if we're talking about money, I can say a grand and you know I mean £1,000. All of these are just a word for an amount of something. A pair, you know I mean 2. A couple, you know I mean 2, etc. So all of these are just names for an amount of substance. And a mole is just a very, 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 very big amount of substance. So, and it's an amount of substance with Avogadro's number. Avogadro's number, also known as capital N, and then it seemed to restart Zoom. Am I back? Is everything all right as far as we're concerned? Hello, 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 hello. Well, apologies if I'm not quite sure. Hopefully I'm sorted. Please let me know if I'm not. My screen seems to just going to double check. Right. Thingy. Just going to double check it is still going. Yes, I think it is. I think it's catching up. Okay, that's fine. Okay, good. Sorry. Cool. It just looked like it was being delayed. So that's all good. Let me go back to the right screen. That one. Apologies for that little intro. I don't know what happened. Zoom restarted itself, I think. Capital N, capital A, but small. Is a number that is good to know off by heart. If you don't, it's not the end of the world. But, you know, it is a good idea to know off by heart because it means we I don't know. Let's do that again. That one. What just happened? It just restarted itself again. It doesn't do that all the way through because that'll be a pain, won't it? Try again. So units of Avogadro's number is per mole because it's number of things per mole. That's what Avogadro's number tells us. It tells us there's 6.02214179 times 10 to the 23 things per mole of stuff. So just to kind of prove that, 1 mole of carbon-12, as in 6.022 times 10 to the 23 atoms of carbon-12, has a mass of 12 grams. Let's do that in blue, actually. 12 grams. So Avogadro worked out that the elements related to one another, relative to 1/12 the mass of carbon-12, in a nice, neat way, which meant if you had 1 mole of any of these elements, it matched their atomic mass, which is very handy. So 1 mole of carbon-12 must contain 6.022144179 times 10 to the 23 atoms. So, quick bit of maths, and I'm going to whiz through it because we are a little bit behind time now. What's the mass of 1 mole of oxygen? 1 mole of iron, 2 moles of helium, 3 moles of hydrogen, and 5 moles of lithium. Can you have a go at working that out? I'm going to give you a minute, or probably less than a minute actually, 10 seconds or so just to have a go at doing that, whilst I double check that we're all okay. I think we are. Yeah, okay, good. So how do we work it out? Oops, sorry, that was just because I moved my screen. How do we work it out? Well, oxygen, we need to use our periodic table because that's incredibly useful. So periodic table, 1 mole of oxygen. It's not oxygen O2. This is just oxygen, the element. So oxygen, the element, will have a mass of 16 grams. So 6.022 times 10 to the 23 atoms of oxygen has a mass of 16 grams. 1 mole of iron, that many particles of iron atoms, has a mass of 55.8 approximately, using your periodic table. 2 moles of helium, or 1 mole of helium, will be 3, I believe. And then, so 2, and I'm actually just going to double check. Helium 3, is it 2? It's 2, isn't it? 4, sorry then. So 1 mole of helium will be 2, so 2 moles of helium, 4 grams. 3 moles of hydrogen. So this is not H2, this is just hydrogen atoms. So 1 mole of hydrogen is 1 gram, so 3 moles, 3 grams. And then 5 moles of lithium. Lithium is 7, I believe. Yeah, 7. So 5 times 7, 35 grams. Hopefully we're super confident with doing that. Please let me know if you're not, but I'm going to swiftly move on just because I don't want us to run out of time, especially if we've had a couple of minor interruptions, which is apologies, but that's the internet's fault. Okay, so let's move. Okay, so how do we relate these things then? How do we relate mass and molar mass? So if you're an equation triangles person, lovely, that's absolutely fine. You can use your equation triangle. If you're not an equation triangle person, then just make sure that you have memorized one of the equations. So mass is equal to molar mass or moles equal to mass over moles. Don't mind, whichever suits you. So you could also use units as well as the other thing. So if you know that molar mass is in grams per mole, if that's all, then all you have to memorize. Grams is mass per mole is moles. So you don't actually have to memorize anything other than molar mass being grams per. And it tells you it's grams mass over mole. Makes it a bit easier. So calculate the molar mass and pop it in the chat if you think you've got an answer. What do we think the mass of 1 mole, sorry, the mass of 1 mole of water is, the molar mass of water? Well, the molar mass of hydrogen is 1. The molar mass of oxygen is 16, using our periodic table this is. For the molar mass of H2O, 2 lots of 1 for water gives us a total of 18 grams per mole. That's a nice one to memorize if you want to memorize it, but you don't have to. It then asks us to calculate the number of moles in 146 grams of HCl. So we're trying to work out the number of moles. So we need mass divided by molar mass. So we've got our mass. We need to work out our molar mass. So again, hydrogen has a molar mass of 1. Chlorine has a molar mass of 35.5, using our periodic table to help us. The mass of 1 mole of chlorine is 35.5. So the molar mass of HCl is 36.5. These are in grams per mole. So if I've got grams per mole and I want moles, then I need to do grams mass divided by molar mass. So 146 grams divided by 36.5 grams per mole. That cancels the grams, brings the moles up onto the top line, which gives me 4 moles of HCl. Hopefully that's super easy. Just have a quick think at how confident you're feeling about that content that we've just covered. So being self-reflective about your revision, about what you're learning, about any classwork, etc., is a really, really good thing to do when you're revising. So make sure you're taking regular checks about how confident you're feeling about your learning. The more confident you're feeling, the longer you should leave it before you do another one. Hello, welcome, welcome. Welcome if you have just joined us. If you are feeling super confused or even just okay about things, then I would recommend giving it a day and then coming back to it. So if you're feeling pretty confident about something, give it a little bit longer and then come back to it, because excuse me, the chances are you would have forgotten something. So doing some questions after a few days, maybe a week and a half, is a really good thing to do. But if you're feeling already super confused, then spending some time as soon as possible to go back over things is a very good idea, good thing to do in your revision. Okay, let's have a go at a quick exam question. This sort of question is the kind of thing which confuses lots of people, so it's a good thing to have a go at. Please feel free to jump ahead and see if you can come up with an answer. When you do, have a think. Does it look reasonable? Does it look like a kind of a normal answer? Does it look like it should be whatever answer you've got? Does it fit? And if so, great. If it doesn't, then maybe have a quick look through, just double check your numbers, your method, just see what you've done. So, solid sulfur exists as a lattice of S8 molecules. Each S8 molecule is a ring of 8 atoms. I mean, they didn't need to tell us that, but they have. Thank you. How many atoms of sulfur are there? And atoms of sulfur are there? Atoms of sulfur there are in that many moles of S8. So first things first, what do we need to do? How would you go about doing this? I think a good place to be would be to work out how many SH molecules there are in 0.012 moles. So how do we do that? We need Avogadro's number. We know I've got 0.012 moles, then how many particles have I got? Let's times them together to work it out. Per mole. Let's give it the full use per mole. Particles, so you can see the units per mole. So if I'm doing the particles, then the per mole and the mole will cancel, and I'll end up with just a number of particles. So what would that be? 7, 2, 2, 6, 4 times 10 to the 21. Particles, what particles are they that we've got here? We're looking at particles or molecules, I could have said, instead of particles, of S8. The question has asked us how many atoms of sulfur there are. So for every particle, every molecule of S8, there are 8 atoms. There are 8 atoms of sulfur in every S8 molecule. So we need 2 times by 8 to get the number of atoms. So 7.22664, can't even copy, times 10 to the 21 times by 8 to give us the number of atoms, gives us 5.78 times 10 to the 22 atoms of sulfur. And that's our final answer. If anyone's not happy with that, just pop a question in the chat. I do try and keep tabs on things, but if I ignore you, feel free to ask twice. If anyone's not happy, yeah, just pop it in the chat. Otherwise, we'll move swiftly on. So just as a sorry, just before I move on, as a quick reminder, the issue here, lots of people will have just gotten to the point of number of particles of S8 and given that as their answer. But of course, they haven't finished yet. So you must make sure you work out the number of atoms of sulfur to make sure you get full marks. Okay, molecular and empirical formula. This is where we're looking at a lot of ratios. So, what is the difference? There is a difference, and you need to know the difference, and you need to know definitions of each as well, because you can be asked about the definition in your exam. So please have a look and make sure that you are confident with your definitions. Molecular formula is the actual number of atoms of each element in a molecule. So the actual number of each in one molecule of that substance. The empirical formula shows the simplest whole number ratio. It's the simplest whole number ratio. So they may be the same as each other, they might not. Let's have a look at some examples. Feel free to jump ahead, see if you can work out the molecular formula and then the empirical formula for these two molecules. I'm going to have a go at it now as well. So molecular formula. How many carbons have we got? 1, 2, 3, 4 carbons. So C4 in a molecule. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. So H8, and then 1, 2 oxygens, O2. Is there anything else in there? Nope, that's it. So the molecular formula, the formula of one molecule of this substance is C4H8O2. But is that the empirical formula? Is that the simplest ratio? So the ratio comes from our molecular formula of carbons to hydrogens to oxygens is 4 to 8 to 2. But I can see already that that's not the simplest ratio. The simplest ratio of carbons to hydrogens 2 to 4 to 1. So the simplest ratio, simplest whole number ratio of elements in this molecule is 2 carbons to 4 hydrogens to 1 oxygen. So here, the empirical formula is different to the molecular formula. H4O. You might be wondering, well, why do I care about the empirical formula? If I know or I can work out a molecular formula, why do we care about empirical formulas? The thing is that a lot of analytical using moles relies on empirical formulae because we are only able to work out, for example, an amount of a substance compared to the other substances in the molecule. So in the substance. So, for example, you might using mass spec, for example, you may determine that there is twice as much carbon as there is oxygen in a molecule, and 4 times as much hydrogen as there is oxygen in a molecule. So that would give us the empirical formula, but it doesn't tell us the molecular formula. So empirical formulas are incredibly important, especially when you go into the lab to do lab work. So what about this other molecule then? What's our molecular formula of this molecule, the one at the bottom? Well, 1, 2, 3, 4 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. And that's it. There's nothing else in the molecule. C4H10. Empirical formula? Well, we're only looking at carbons to hydrogens now. So we've got 4 to 10. And again, I can see nice and easily the ratio. I can just halve both of them to get a ratio of 2 to 5. I can't go any smaller than that. If I went any smaller than that, it'd be 1 to 2.5 hydrogens, 1 carbon to every 2.5 hydrogens. And that's not a whole number ratio. So that's not my empirical formula, because empirical formula shows a whole number ratio. So C2H5 for my formula. Common error in an exam is not doing the final step, is working out a ratio of a substance and then not writing it out as the formula. Notice these are called molecular formula, empirical formula. So you need to give the formula. You need to give C2H5 as your answer, not just the ratio of 2 to 5. You have to give it as C2H5, for example. Okay, let's keep going. How do we find empirical formula? So one of the things that we can do is when you're in a laboratory is you can work out your amounts of a substance, and then you can use that to determine the empirical formula of a substance. So you may or may not have had the opportunity, possibly even at GCSE, to do a practical that involved burning magnesium in a little crucible, and you could work out the mass of magnesium that you burnt. You could work out the mass change, so how much oxygen had been gained by that magnesium. And then using those two amounts, you could therefore work out the ratio of elements in magnesium oxide, the product of combustion of magnesium. So you might have had the opportunity to do that in GCSE. You might not have, but hopefully you did. But there are similar experiments that you can do to determine masses. So in this one, in an experiment, 2.025 grams of magnesium reacts with 13.3 grams of bromine. Work out or determine the empirical formula. So we need to work out the ratio of atoms of the elements. So that means we're going to need to use our molar equation, our Avogadro's constant equation, to determine how many moles of each we've got. So what's our equation? Our equation is mass is equal to molar mass times moles. So in this case, what do we need? Magnesium. Let's work out magnesium first. So the molar mass of magnesium using our periodic table should be approximately 24.3. Just use whatever you're given on your data sheet. molar mass, what we're doing, bromine, is 79.9 grams. So if we wanted to work out how many moles of magnesium there were, so 2.025 grams, right, units there, those are grams per mole. So if I do grams, whoops, not times, divided by molar mass, so 24.3 grams per mole, I get grams divided by grams, they cancel. That brings the moles up onto the top line, so I end up with just mole, so 0.083 mole of magnesium. And then the bromine, how much bromine have I added? Well, 13.3 grams divided by 79.9 grams per mole gives me 0.166 moles of bromine. So that tells me that my ratio of magnesium to bromine in molar amounts, because of course we can't use the masses as a ratio because the atoms, the mass of each atom is different. So it doesn't tell me how many atoms of each are in ratio to one another. So I need to use moles to determine my ratios, my molar ratios. So that would be 0.083 to 0.166. Now I can see already that there's a relationship, but if you're not sure and you don't know how to work it out, if you're ever working out ratios, you can always just divide by the smallest number. So my smallest number here is 0.083. So if I divide them both by 0.083, I end up with my ratio of magnesium to bromine. 0.083 divided by 0.083 gives me 1. And 0.166 divided by 0.083 gives me 2. The reason you divide by the smallest number is so you always end up with a ratio to 1. And then you're comparing how much bigger the others are to the one that you've divided by itself. So we've got twice as much bromine as we do magnesium. That means my empirical formula is MgBr2. And if we know our ions, if we know ionic formulae, we can have a look and determine that that does seem reasonable actually, because magnesium forms a 2+ ion, bromine usually forms a 1- ion, so you're going to need 2 to cancel out the +2 on magnesium. So MgBr2 makes sense. Awesome. Again, if you have any questions, pop it in the chat. Otherwise, we're going to keep moving forwards. Oops. Again, please feel free to zip on ahead if you want to, come up with an answer. Again, you can pop it in the chat. Otherwise, I'm going to work my way through slowly. So in an experiment, the percentage composition of the sample was 60% carbon, 13.3% hydrogen, and 26.6% oxygen. The relative molecular mass of the sample was, so this is a common exam question and something that confuses students sometimes, but once you've gotten into the habit of it, it's actually really easy. So first of all, if you've been asked to work out molecular formula, but you've only been given percentage compositions, either by with a percent or with a mass, sometimes you can be given mass compositions. First thing we need to do is work out an empirical formula. Once we've worked out the empirical formula, we can then work out the molecular formula. And a nice way to kind of think about it is whenever you come up with a question like this and you think it's got something to do with moles, see if you can work out how many moles of something you've got. Now, here we're given percentages, which might throw some people off because we're not used to dealing with percentages, we're used to dealing with masses in order to work out moles. But all we've got to do, it's quite simple, is we've got to pretend that we've got 100 grams of the substance. Because if we know the percentage composition, if we've got 100 grams of the substance, then we know that 60%, i.e. 60 grams, is oxygen. 13.3%, i.e. 13.3 grams of 100 grams is hydrogen, and 26.6%, i.e. 26.6 grams of our 100 grams is oxygen. Oh, I put oxygen first. That should have been carbon. 60 grams of carbon. Apologies. There, 60 grams of carbon. So if you've been given a percentage composition, you just have to pretend that you've got 100 grams and then you work out the mass composition, because the percentages convert directly to masses if you've got 100 grams of something. And it should approximately work out to be 100. If you're off by a large amount, chances are you haven't recognized that they maybe didn't give you a percentage composition, a percentage amount of, say, hydrogen in a hydrocarbon. They might have only given you the percentage composition of carbon in a hydrocarbon. So if it's not 100%, the rest of it, the rest of whatever it is, must be made up of hydrogen. Here, it looks like they have approximately given us the right numbers. There's just a 0.1% out, and that'll just be because of rounding numbers, rounding errors. So I'm not worried about that. So let's have a look at it together then. If I've got 60 grams of carbon, if I do equation, so we've got mass is equal to molar mass times moles. So I'm trying to work out the moles of carbon. So I've got 60 grams divided by 12 for carbon. I've got 13.3 grams of hydrogen divided by 1 for hydrogen. And then I've got 26.6 divided by 16 for oxygen. If we wanted to do this the long-winded way, we would work out our amounts, whatever our amounts were, and that would be our empirical formula. Now, and that's absolutely fine. We can do that thing. Actually, in fact, let's do that. I was going to try and kind of add in a skip step, but we won't. I won't overcomplicate things. So let's just, let's work out those amounts. Sorry, I forgot to put my units in. Grams per mole. So that's carbon, that's hydrogen, that's oxygen. So I've got 5 moles of carbon to every 13.3, try that again, 13.3 moles of hydrogen to every 1.6625 moles of oxygen. If we wanted to make them as a ratio to 1, we would divide them all by the smallest number. So we would get 1 mole of oxygen, 13.3 divided by 1.6625 is 8. And then 5 divided by 1.6625 is 3. It's 3.0075, but that's so close to 3 because you've got 2 decimal places and then a number. It's so close to 3, we can easily round it. Don't round something that's a mole and a half, because it's halfway between 2 molar numbers. But 3.0075 is so close to 3, it is quite easy to be rounded. So we divided by 1.6625, divided by 1.6625, divided by 1.6625. Oopsies, no. I don't know why it's doing that. Sorry. Let's go back. Shouldn't have done that. There we go. I think it thought I was pressing a button, which I wasn't. So then we've got our ratio. Our empirical formula is 3. Whoops, no, let's write it out properly. Our empirical formula is C3H8O. But how do we work out what our molecular formula is? Well, the molecular mass, the relative molecular mass is 60, which means that the mass of one molecule of the substance is 60. So the best thing to do then is to work out what the mass of one lot of your empirical formula is. So that would be 3 lots of 12 plus 8 lots of 1 plus 16. And that actually gives us 60. So the mass of the empirical formula is 60. Therefore, the molecular formula must also be the empirical formula. They must be the same. C3H8O. If, for example, it said that the relative molecular mass was 120, we would know that the empirical formula is the molecular formula is twice the empirical formula, because our empirical formula would have had the mass of one lot of the empirical formula would be half the mass of the molecular formula. But in this case, they're the same, because one lot of our empirical formula is 60, the molecular formula is 60, so it's telling us that one molecule is the same mass as the empirical formula, so it must be the same. Is anybody not happy with any of that and wants to ask a question about that? So we've worked out the ratio between the two, the ratio between the relative molecular mass and the mass of the empirical formula. And it's a 1-to-1 ratio, which means the molecular formula is the same as the empirical formula. Easy peasy. Okay. Again, have a quick think about how you're feeling. Hopefully you're feeling nice and confident about it. But if you're not, then maybe make a note about what it is that you're not feeling confident about so you can come back to it. You can still ask questions if you have questions in the chat, but otherwise we're going to have a go at a last couple of exam questions before we finish. So, sodium burns in oxygen to give a pale yellow solid X. 1.73 grams of sodium reacts with 1.2 grams of oxygen. Calculate the empirical formula of X. We've got gram amounts, but if we're looking at empirical formula, it's a ratio of moles. So we're looking for a ratio of moles. So all we need to do is work out our ratio of moles. Sodium to oxygen. So we've got 1.73 grams of sodium, 1.20 grams of oxygen. So sodium has a relative molecular mass of 23 grams per mole. So 1.73 divided by 23 gives us 0.075 mole of sodium. I'm just going to move that over actually, a bit in the way. 1.20 grams of oxygen. Oxygen has a relative molecular mass of 16 grams per mole. Grams divided by grams per mole gives me moles, and that's 0.075 mole. So my ratio of moles of sodium to oxygen is 0.075 to 0.075. Let's try and write that properly, which is 1-to-1. Again, I could divide by the smallest number, which is 0.075, to get my ratio of 1-to-1, but I haven't finished. Don't forget they've asked for empirical formula, so you have to give a formula, which in this case is NaO, and that's the answer, not the ratio of 1-to-1. So don't forget that, because sometimes, especially if it's a 1-mark question, you don't get the mark. So just got to be careful. Part 2 says the molar mass of X is 78 grams per mole. Give the molecular formula of X. So we've got the empirical formula. We're now trying to work out the molecular formula. We know the molecular mass is 78. So how much does NaO? What is the molecular mass of NaO then? 1 lot of sodium and 1 lot of oxygen. 23 plus 16 is only 39. The molecular mass is 78, but 1 lot of NaO is only 39. So the ratio of 78 to 39 is 2-to-1, which means the ratio of the molecular formula to the empirical formula is 2-to-1. That means my molecular formula is 2 lots of the empirical formula, which in this case is Na2O2. And that's our molecular formula, Na2O2. Hopefully everyone's happy. If you're not, put a question in the chat, otherwise we're going to keep moving forwards to our final exam question. So sulfamic acid might not be something that we've met yet. That's absolutely fine. We don't have to have met it. They're giving us the context and they will give us all the information we need to answer the question. It might be a weird context. We might feel a little bit put off by it, but we have to be confident and we have to know in ourselves they will have given us enough information to answer the question. So sulfamic acid contains 14.42% by mass of nitrogen. Oops, it's trying to, what's it trying to do? Oh, sorry, I think it tried to shut down the PowerPoint. Back. 14.42% by mass of nitrogen, 3.09% by mass of hydrogen, and 33.06% by mass of sulfur. The remainder is oxygen. They've told us the remainder is oxygen, which is kind of them. So we've got nitrogen. Oh, I've gone red again. Let's go back to blue. I've got nitrogen to hydrogen to sulfur to oxygen. So the first thing to do will be to work out what the remainder is. So nitrogen plus hydrogen plus sulfur, 14.42 plus 3.09 plus 33.06. Whatever that is. I don't actually have that number in front of me, so let's just work it out. 14.42 plus 3.09 plus 33.06, 50.57. 50.57. So the remainder is oxygen. So 100 minus 50.57 will give me how much oxygen I've got. So 49.43 oxygen. You could have done that in one calculation if you'd wanted to. That's absolutely fine, but I'm trying to do it slowly so that you can see my workings out. So my nitrogen is 14.42. If I had 100 grams, there would be 14.42 grams of nitrogen, 3.09 grams of hydrogen, 33.06 grams of sulfur, and therefore I'm looking for the empirical formula, so I'm looking for a ratio of moles, so I need to convert to moles. So my mass divided by my molar mass of nitrogen, which is 14. At least 2 decimal places when you're doing this. So I can't round that to Yes. Okay, I think we're better now. I think it's better. Get through it. We will. Apologies for that again. I don't know why it thinks that it's having issues. I've got Wi-Fi. I'm wondering, this laptop sometimes decides it wants to just restart, and it told me just I don't know, I'm really sorry. I don't know what's happening. It hasn't. It's just keeps trying to restart itself, and I've lost all use of my mouse. So we might have to end it there. What I've done, if it'll let me share, just kind of scribble an answer for the first one, NH3SO3 for part one. And then if you were to go on and do the second bit, you'll realize that the mass of the empirical formula is the same as the molecular formula. So I think we're going to have to end it there. Hopefully you have gotten to the end of that. Apologies for the technology issues. I've got no idea why it's decided to play up. It should be absolutely fine. So the laptop wants to restart itself and it's throwing a hissy fit. I didn't let it 2 minutes before it started. But please have a look on the schedule, have a look at any future web classes or previous web classes, and I hope to see you at some point soon. Again, apologies, but thank you very much for sticking with us if you did. And we will see you as soon as possible. Okay, thank you very much, guys. Apologies again. Bye.